Hello all, welcome to pericyclic reactions part 6. We will be dealing with electrocyclic reactions in this video as well. This question, it is from CSIR Net, December 2013. The conditions A and B, here is the condition A and B required for following pericyclic reactions are, there are several reaction conditions given, thermal conditions both, one photochemical, B as thermal, etc are given, that we have to check which are the suitable conditions A and B. How many electron system here, that we will check. Here it is 2 electrons, 3, 4, 5, 6, 7, 8. So here we are having 8 pi electron. Okay, that means we have to check for 1,3 butadiene. We have to check for 1,3 butadiene case. Just remember multiples of 4, that is 4, 8, 12, all are electrons I am talking about, and so on, 16, 20, multiples of 4. If the pi electrons are multiples of 4, then we should check for the case of 1,3 butadiene. In case they are 4n plus 2 pi electron, that is 6, 10 electron, or maybe 14 electron, etc, then we, in this case, we go for 135 hexatriene. So just remember this part, multiples of 1,3 butadiene. If they are 4n plus 2 pi electron, then we go for 135 hexatriene, the HOMO of it. This is the molecular orbital diagram for 1,3 butadiene. If we go for the photochemical part, then we have 4 electrons to distribute, and 4 electrons, it gets distributed in this way. So this part, this becomes the HOMO. So this part is the new HOMO, that is the highest occupied molecular orbital. So we are concerned only about the end carbons. How are the phases distributed? So here we are having positive phase on top, and at this end carbon also positive phase, it is on, both the positive phases are on top, so I am drawing it on top. Now regarding let us get back to our question. In this part, if you are observing this part, this Me, it is cis to each other, and if you observe this part, it is trans to each other. So remember this stereochemistry, one part it is cis, another it is trans. I'll just remove this part. We are no longer in need of this information, so I'll remove it. So let's draw this part. We are having a double bond here, double bond, double bond, double bond, and then regarding this part, we are having a trans Me. Look here, we are having a trans Me, and in this part we are having a cis Me. Cis to what? Cis to this bond, and there is a hydrogen here if you are aware of it. Just now I had mentioned that the phases, the end carbon phases, here it was positive phase on top, here also the positive phase was on top. Very important, the end lobes, the positive phases were on top. Now how the reaction will happen? Since the positive phases, they have to come in contact, in close proximity. If I rotate it in clockwise direction, so it will come in this way, and if I rotate this in anti-clockwise direction, the positive phase, they come in contact with each other, and this will be constructing, forming a sigma bond. Now what happened to this Me? See, I am rotating the lobes in clockwise direction, so this Me will go on top. Very important, since I am rotating in clockwise direction, this Me goes on top. I hope you are getting it, why this Me went on top, because I am rotating it in the clockwise direction. Now what happened to this Me? Since I am rotating it in anti-clockwise direction, this way, this Me is to be rotated in this way, okay, in a circular motion. So what will happen, the Me that was here, it will go in this way. Now if you are carefully observing the stereochemistry, both are on the opposite side, which means they are trans to each other as we are in need of it. Okay, the rest part you can draw it later. Okay, I'll draw it now. This double bond falls here, this double bond falls here, this double bond falls here, and this double bond that was here, it forms a sigma bond here. So we will have a double bond here, a double bond here, and a double bond here, and this is the sigma, new sigma bond that is being created. So what is the stereochemistry of the two Me over here? The Me, they are trans to each other since they are on the opposite sides. The HOMO over here, that we had selected was from photochemical condition, right? Photochemical. So it will be H nu. So A is H nu. This we have to remember. A is H nu only, then we will get the trans over here. In the next part, this is the case. This is 135 hexatriene case. Okay, so we have to check for the HOMO of the 135 hexatriene case. And another thing is that we need cis hydrogen, and in my previous video, if you can check, the link will be over here, or check all my previous videos regarding pericyclic reaction, then you will come to know for cis hydrogens over here, we should be thermal condition. Okay, thermal means ground state. If you are not sure, I'll explain it again. This is the molecular orbital diagram for 135 hexatriene. That is our case now. And since ground state, the HOMO, it is here. What are the phases of the end lobes and carbon? Both the positive phases on top. So here we are having positive phases on top. So let's get back to our question. Okay, so here if I draw the positive phase on top, hydrogens, they are here. Both hydrogens are trans to each other. The stereochemistry of the hydrogen, it is trans and it is trans. Suppose I want to bring the positive phases on same, I go for this rotation, that is in thermal condition. In thermal, that is delta, and it is disrot motion. Both the positive phases, they can meet. Yes, they have to meet positive. What happened to this hydrogen? Since it was we are rotating it in the clockwise direction, the hydrogen went on top. This hydrogen, since we are rotating in anti-clockwise, it goes on top. Yes, so here, see both the hydrogens are on the same side. So this is the condition. So here H nu, and in this case it will be thermal. So option B, option 2, that is A H nu, B is thermal, that is the right choice.